Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. This time we're going to be talking about neutron stars and pulsars. These are the massive cores of massive stars after they have died. So this is an amazing set of things. Last time we talked about white dwarfs and what they can turn into. We only said they were the low mass or medium mass stars, but now let's look at the ultra rare type stars and what they do. So once again, let's go back and look at our life cycles of stars thing. We have basically 6 layers that we talked about. At the bottom are the lowest mass stars, which are barely stars at all. They're effectively not even stars because they don't even do nuclear fusion in the core. Those are the brown dwarfs. Red dwarfs are the G and the K and M type dwarf type stars. They just burn for up to 1 trillion years and then eventually become white dwarfs and just fade away into obscurity. Something like the sun, or a little bit more massive the sun, between, say, the sun's mass and up to about 8 solar masses. A sun-like star will live a few billion years. The sun will live 10 billion years. More massive stars live shorter. They become a planetary nebula and make a white dwarf. And if they're in a companion, do a supernova. But now we're going to be talking about the next level up. Much more massive stars. Stars more massive than the sun that then turn into giants and then blue supergiants and then explode into a nova, which we talked about last time, a supernova explosion. And now we're going to see what the remnant is, a neutron star. And that's what we see in this thing. The other 2 things we'll talk about next time. All right, so neutron stars, after a type 1 supernova, which is a white dwarf having so much stuff that piles on top of it that it explodes under the Chandrasekhar limit. A type 2 supernova is a supermassive star that gets compressed down into the core, and that core material then becomes a neutron star. And what are neutron stars? They are the remnant cores of supermassive type stars. Well, supermassive meaning about 8 or somewhere between 10 and 20 solar masses as the original star. And when the supernova occurs, there is a bit of a leftover piece. Remember we said in the supernova lecture that there's a core bounce as everything gets to be this incredibly high density down in the core during the supernova. And so this thing that happens is they get compressed so incredibly tensely that we now, instead of having electron degeneracy, which we talked about in a previous lecture, now we have neutron degeneracy. And so this is the same thing as electron degeneracy, except it is done with neutrons. So instead of the electrons holding it all up, and just kind of, and their pressure is no longer dependent on the temperature. Now the neutrons and the electrons and protons merged together to form neutrons, and then those things then support the entire mass of the star. What's left of a stellar core from a star that originally was between 8 and 18 solar masses, the remnant is between 1.2 and about 2 solar masses, but it's really not well known. The radius is about 10 kilometers, which is very small, and the density is enormous, about 10 to the 14th grams per cubic centimeter, which is gargantuan. Funny thing is that something that's that massive, 2 solar masses compressed down to 10 kilometers, the escape speed then is really big, about 70% the speed of light, and it has amazing results. And there's no nuclear fusion happening in this thing, or any gravitational contraction. It is being held up by the neutron degeneracy pressure. It won't contract under gravity anymore because that pressure is holding it up. And there is, even though the effective temperature is extraordinarily high, there is no longer nuclear fusion occurring in it. And so there is residual heat that happen with this thing, and they glow with the residual heat. However, they're really tiny, so their luminosity is incredibly small. How small? Remember, these objects are about the size of the island of Manhattan, about 10 miles or so across, about 10 kilometers across, and say the mass is about 1.5 times the mass of the sun, which is about 10, and that's an incredibly packed object. So, and the escape speed is about 0.7 c, or about 70% the speed of light. So these things are tiny. And they're about 1.3 solar masses. They're incredibly dense. If a neutron star were to rest on top of Queens and Long Island, there wouldn't be anything left of the Earth. I mean, nothing. There would be nothing. Couldn't hold it up. The Earth ain't that strong. it would be on the surface of the white dwarf. It would, so if you Google Discovery Channel and look at neutron star colliding Earth, you'll find a crazy, crazy, crazy video on Discovery Channel that shows what happens when a neutron star collides with Earth. Basically, the Earth falls onto the surface and is torn into shreds and becomes a skin only a couple of centimeters thick on the surface of the white dwarf. That's what would become of the Earth if this situation that we see in this image happened. That would be bad. Yet another of the million ways to die in astronomy. All right. So let's talk about the ranges of masses for neutron stars. They range in mass roughly between 1.1 and 3 solar masses. It's not incredibly well known, but that's the observed maximum mass. The theoretical mass is between 1 and 3. But the maximum observed mass is about just a little bit over 2 solar masses. And remember that any compact star smaller than 1.44 solar masses, which is the Chandrasekhar limit, the Chandrasekhar limit is the limit of electron degeneracy as the electrons get closer and closer and closer to the speed of light. And so once the electrons are moving at the speed of light, they can't support it anymore because that's the maximum possible energy that they can have. So then the star is collapsing and collapsing and collapsing, and the electrons are moving faster and faster and faster. So that is the maximum limit that a white dwarf can have. However, if they merge together, they can form a neutron star. Now, if it approaches the Chandrasekhar limit as a white dwarf, it'll explode. But if it collapses under the power of a type 1, type 2 supernova, then it can exceed 1.4 solar masses and go between 1.4 and 3 solar masses, which is called the Tolman-Oppenheimer-Volkoff limit, which is the similar thing to Chandrasekhar limit, except now, instead of electron degeneracy, it is neutron degeneracy. So go back and look at my really long lecture on the nature of electron degeneracy and the previous one on white dwarfs to know what I mean by that. I'm not going to go over that again here. So neutron degeneracy is basically the same thing. It's a similar structure as electron degeneracy, except that the pressure is so high that the protons and electrons merge together to form neutrons, and then that is the link that pushes them all together. So then there if it's above 3 solar masses, then it could be, there are other things that potentially smaller than neutron stars, and the neutrons can have maybe what we call quark stars, where it's not neutron degeneracy that holds it up, but quark degeneracy. And what are quarks? Quarks are the constituents of neutrons and protons. However, there's no objects that are known that could possibly be a quark star, because the maximum observed compact star is about 2.01 solar masses. Beyond 10 solar masses, nothing's going to win. And you have what's called neutron degeneracy pressure. No matter what, will lose, and it will have to collapse to a black hole. So let's see what that works out to be. But neutron stars, when they collapse down to these really, really, really tiny objects, the gravitational field becomes catastrophically large. The field is so big, it's over 200 billion times stronger than the Earth's gravitational field. Well, okay, oops, I made a mistake here. Got a typo. Actually, the typo is that not the star's magnetic field, but the neutron star's gravitational field. It's insanely powerful, over 200 billion times. Remember, magnetic fields are different than gravitational fields. So if you're just looking at the words, you're going to see I have a mistake. And I'm not going to stop this lecture just because of this mistake. I'm just going to keep going on because here we go. Should have got that at the beginning, but hey, whatever. It's live theater, right? So if the gravitational field is over 200 billion times stronger than the Earth, then nothing could resist the gravitational force of that, and it will be smashed to a complete pulp. And by pulp, I mean all the atoms inside it get ripped apart in very strange ways. So if you had something on the surface of a neutron star, Superman wouldn't even make it, but let's say something was 1 meter above the surface of a 12-kilometer radius neutron star. If you dropped it from a height of 1 meter, by the time it hit the surface of the neutron star, 1 meter down, it would be going 1,400 kilometers per second. But even before it hit the ground, hit the surface, the tidal forces would stretch that thing apart, whatever it is, and would actually turn it into a spaghetti thing. So even if it was something as small as a golf ball, that golf ball would become a spaghetti string, meaning the top of the golf ball would be stretched away from the bottom of the golf ball. And the force or the energy released by that would be greater than all of the nuclear bombs ever exploded on the surface of the Earth in the history of the Earth. In fact, that would be about the same amount of energy that the sun emits in a few minutes, if not more. I should have calculated that. That's a great calculation. In fact, I will leave that as an exercise to the student. But but there's an enormous amount of energy that is put there. So we can say an object dropping inside of this will go to 1,400 kilometers per second. And if you want to have some fun, you can see the kinetic energy of that by saying, well, what would 1 kilogram dropped? If its kinetic energy is the mass times the speed squared, what do you get out of that? What's the total amount of energy? And it's an enormous amount of energy that you get. Anyway, so the time dilation, because of general relativity comes into play, there is actually a time dilation. At the surface of a neutron star, if you had a clock, that clock, if 8 years passed on the surface of the neutron star, yet very, 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 very far away here on Earth, where the gravitational field is much less, or even just like a couple of light years away from the neutron star, 8 years on the surface of the neutron star means 10 years far away from the neutron star, which is very interesting. So there is a time dilation between the surface of the neutron star and far away. So time runs slower on the surface of the neutron star, which is fascinating. There's also gravitational lensing that occurs because the path that light takes as it tries to leave the surface of a neutron star, let's say a little gamma ray gets emitted, it will, if it gets emitted at an angle that's not specifically perpendicular to the surface of the neutron star, it'll start to curve in its path. In fact, what we see in this crazy little image here is what it would look like that if you were at a relatively massive neutron star, you can actually see around the backside of the neutron star because of the bending of the light due to the gravitational field. So each one of these square degrees is 30 square degrees. But you can see past the poles on both sides. So it looks like you can see more. Now, if the radius of the neutron star is actually much smaller, because the mass is higher, then you could actually be at a certain place above the neutron star and see the entire neutron star, the front and back, the entire neutron star in your full field of view, because the light could be possibly trapped in a circular path around it. And that can happen due to gravitational lensing at certain radii, meaning the neutron stars could be very, very massive. All right, so when you take an object like the sun and compress it down, if you took the sun, a whole solar mass, and compressed it down to something 10 kilometers in size, then you're going to spin it faster. It will spin faster, and that's called the conservation of angular momentum. So angular momentum does get conserved, and so what is angular momentum? Angular momentum is the product of the mass times the radius times the rotation speed, and that's in very, very, very general terms. So if you keep the mass the same, and angular momentum is conserved because there's nothing keep pushing the angular momentum away, so that is conserved for a given mass, radius, and rotation speed. So if that number for the angular momentum stays the same and the mass stays the same, and you shrink the radius, therefore the rotation speed has to go way up. So the period of rotation is going to go faster. It'll get faster and faster and faster as it gets smaller and smaller and smaller. So if you took the sun, which is rotating at the equator every, say, month or so, and if you shrank it to the size of 12 kilometers, it would be spinning about every millisecond or so. And the fastest spinning neutron star is that one with that crazy name, and it rotates about 43,000 revolutions per minute, or 716 times a second. That neutron star is actually spinning faster than a helicopter blade. Helicopters don't spin 700 times a second. They spin a few times a second. They do not spin that fast. So neutron stars, things more massive than the sun, spin faster than helicopter blades. In fact, the linear speed of that neutron star is about a quarter of the speed of light. That's how fast it's rotating. Now, eventually neutron stars do slow down or spin down because they have incredibly strong magnetic fields, and their magnetic fields interact with the interstellar medium. They also can create light as they spin, and that electromagnetic radiation carries away the energy of it, and that allows the magnetic field to interact with it, and therefore carry away the rotational speed or carry away angular momentum by emitting light, which is really interesting. The magnetic field can be so strong it carries away the angular momentum. All right. So now the surface of a neutron star, or even inside a neutron star, is incredibly hot. Remember, they're formed in the forges of supermassive explosions of supernovae. And so we have, when they're formed, they can be formed around almost 1 trillion Kelvin, which is just a catastrophically large number. What is that? We can't even put our hands around that. There's no way to really know what that means. However, they keep emitting neutrinos as they do and as they collapse. And so as even in this temperature, the temperature is so high that that actually induces nuclear reactions that carry away energy by neutrinos. So neutron stars fall very, very, very quickly down to only about 1 million Kelvin, which is still hotter than any other star out there. And what that does is that this lower temperature of 1 million Kelvin means that their peak wavelength of radiation is way out in the X-rays. And that is, if we assume that the neutron star is at the same temperature and that is thermalized, meaning it has a black body spectrum, then we can use the lambda max equals b over t thing that we learned way back, which is Wien's law, and the Stefan-Boltzmann law to determine the luminosity of it given the radius. And we find if we know the peak wavelength out in X-rays, that gives us a very, very, very high temperature, but the radius is insanely small. So that means the luminosity is really tiny. So these things, even though the luminosity should be incredibly bright because of the temperature, the radius more than undoes the effect of that. So the luminosity of these things is very, very, very small. And just to give you an idea, that inset is a graph of, some typical cool stars that are between 3,000 and 6,000 Kelvin. The emission from X-rays would be really huge because they would be in millions of Kelvin, which would make these graphs look like little tiny bumps, and these would look like a tiny bump next to a mountain, which would be how big these bumps would be. But that would be over a small amount of surface area, and the surface area is really small, so the luminosity is tiny. So the temperatures are really hot. Now, here's a really cool thing. When you take something and you make it really small, you have a huge amount of mass, and you compress it into a very small volume, you raise its density. And so the densities of neutron stars are really big, like 10 to the 17th kilograms per square meter, that's insane. It's 100,000 billion times the density of the center of the sun. Okay, that's what 10 to the 14th times the density of the sun means. The sun it's more than 100,000 billion times the density in the center of the sun. Isn't that wild? That's just out of control, which is the same density as an atomic nucleus, roughly speaking. So a neutron star is so dense that 1 teaspoon, which is about the same size as a cube of sugar, would have a mass of the tallest mountain on Earth, all of Mount Everest, all in one place. So take Mount Everest, compress it down to something half the size of a cube of sugar, and you've got the density of a neutron star. Now, that means the pressures are incredibly, incredibly high. Just one last thing about the density. If you go and look at Marvel Comics, shows the character Thor. Thor, the god of thunder, his hammer is made out of a neutron star. Yeah, that'd be pretty tough to lift unless you were a god. So luckily, Thor's a god, so he can lift a neutron star. But by rights, nothing else can lift it. And somehow, something with that density somehow doesn't do anything when he sets it on a table or puts it on somebody. Yeah, it should have such an incredible gravitational interaction that it pretty much destroys everything around it. So somehow, it can't be lifted by anybody, but yet he can set it down on a table or on the floor of a building. It's really kind of weird. It's just, how can you set it down on anything and have it not go right to the center of that thing? Well, hey, it's comics. What can you say? All right, but that's kind of fun to think. In any event, we can then look at the pressures that happen. And I found a really cool list of pressures. So it's fun to think that 1,000 pascals, where a pascal is a measurement of pressure. So your lung pressure when you breathe is about 1,000 pascals. About 10 times that is heart pressure. About a million pascals, or 1,000 times your lung pressure, is about as hard as you can bite. Or more specifically, if you put a zillion people biting on a nuclear submarine, that's about this pressure that the nuclear submarine's hull can take. And that's the same as a nuclear class submarine can take if it goes down about 500 meters. That's about a million pascal. Funny though, is that you can also then take lots of women in stiletto heels and have them all walk on the surface of the submarine. Now, if all these stiletto heels where women were walking such that they all stomped with their stiletto heels so there was no free space on the surface of a submarine, they would crush the submarine because a normal woman in stiletto heels is 10 million pascals. So if many women, so that all their heels were linked together so there was no space between them, all hit the sides of a submarine at once, it'd crush it. Interesting. Power to stiletto heels. So 100 million times the 100 million pascals is the bottom of the Marianas Trench. So really, that's a huge amount of pressure. 10 billion pascals need to make diamonds, only 1,000 times more than what is made by women walking in stiletto heels. Fascinating. The pressure of a nuclear bomb is 10 to the 15th pascal, which is 10,000 times what it is at the center of the Earth. 10 times greater than a nuclear bomb is what the center of the sun. Well, now we're getting up to insane numbers. 10 to the 23rd pascal is the center of a Chandrasekhar limit solar mass white dwarf. Chandrasekhar mass white dwarf. 10 to the 31st is the surface of the neutron star, and 10 to the 34th pascals is the core of a neutron star. There's just really nothing to think about these things. It's just very strange. So because remember that the equation of state for materials links density, pressure, and temperature. Under these incredible conditions, there's no way to really get there's no really good state of matter at these densities. So it's all very theoretical, and you have to take into account quantum chromodynamics, general relativity, lots of things in order to actually understand what's going on, the strong nuclear force. And it just is a real mess to try to understand what's happening down there. So the equation of state and exactly how they go is not well known. We don't have it like we have in the previous lecture for white dwarfs approaching the Chandrasekhar limit. All right, so the other thing is that we talked initially about the sun with its magnetic field. Likewise, stars have magnetic fields. So there should be a magnetic field, and so the magnetic field becomes wildly strong as the neutron star collapses. So it's hard to know what magnetic field kind of strengths are, but the fun thing is we can say the 32 micro Tesla. So the Tesla is a unit of magnetic field, and it's the SI unit of magnetic field. So 32 micro Tesla is the strength of the Earth's magnetic field. So if you pull out a compass and just say what's north, that's why you have to have a very balanced thing, because it can get messed up by other magnetic fields around you. And if you bring a refrigerator magnet next to it, which is 5 millitesla, which is 100 times stronger than the Earth's magnetic field, then a typical compass will point at it. So that's 5 millitesla. And the sunspots on the surface of the sun are about 3/10 of a Tesla. And those things actually serve to show you the Zeeman effect, which actually can be measured. So that's actually a pretty strong magnetic field, is 3/10 of a Tesla. Then the very strong like 1 1/4 Tesla, is what you have with very strong magnets that you can buy, say, off of Amazon, 1 1/4. And if you go and buy, if you go like take apart a loudspeaker, like some big like a big audio loudspeaker, and then look at the coil gap that they have inside of there, inside the gap, that's even stronger. Again, it's about 2 Tesla. If you go get magneto MRI at a lab, you're going to be experiencing about a 3 Tesla thing, and some of those can go up to 17 Tesla. The Large Hadron Collider has magnets that are about 8 Tesla, and those things serve to confine extraordinarily hot plasmas, and they can bend the paths of protons and electrons going at nearly the speed of light. That's what 8 Tesla can do, and they're some of the strongest magnets known. But the ITER experiment, which is its goal is to try to instantiate nuclear fusion, and that's what the superconducting magnet system is for ITER. Those are only 13 meg Tesla. 16 is kind of a funny thing. There's some really funny videos about you can levitate a frog with 16 Tesla. And the water molecules will actually align and then go against the magnetic field, and that makes the frog float. So have some fun. Google floating magnetic frog, and you'll see some funny videos. A little bit stronger than that is our experimental magnetic resonance imaging, which is the strongest strongest superconductor in a lab. And the maximum strength for short period magnets is about 27, and 45 is continuous. 100 is the surface of a white dwarf. But neutron stars have 10,000 to 100 million Tesla. There is literally nothing else out there that does this thing. That the sun can't do it, white dwarfs can't do it, nothing can do this except neutron stars. And magnetars, which are supremely magnetic neutron stars, are between 100 million and 10 billion Tesla. Now, if we then say, wow, how big is this magnetic field? If we took a magnetar at the top end of that range, which is, say, 100 billion Tesla, and that neutron star passed within the orbit of Pluto, that would demagnetize every hard drive on Earth at 40 astronomical units. That would be a bad day. So, yeah, these things are insane magnets. So they would have visible effects on the solar system at 1 light year away, a magnetar would. So if they got really close, it would be bad. So let's look at those things. These things are really bad. So let's say the magnetars are incredibly strong, and they are possibly the sources of particular gamma ray bursts called soft gamma ray repeaters or anomalous X-ray pulsars. So what's happening with these magnetic fields that become that strong? The magnetic fields can be so incredibly strong that the energy density inside the magnetic field is larger than is required of ordinary matter. So we can say, what is E equals mc squared for a proton? What is E equals mc squared for an electron? And the magnetic field itself in space exceeds that of the energy of an electron and proton in mass. And what it can do is that the magnetic field can polarize the vacuum. In fact, the vacuum of space itself then becomes polarized by the magnetic field, and the space itself becomes what's called birefringent. And birefringent means that space itself has multiple ways that it can refract light. So go back and look at our refraction. We think of a refracting telescope. It refracts the light. It changes the direction. So when it's birefringent, it depends on the polarization of the light, and depending on the polarization of the light, a photon can be split apart, and the light can be split apart or forced to merge. And if photons can be forced to merge, then they can create particle-antiparticle pairs, such as protons and antiprotons, or electrons and anti-electrons, which is really crazy. Once those things are created, then those proton-antiproton pairs can then recollide and form gamma rays. Also, such strong magnetic fields take atoms and they force the atoms to become, instead of spheres, the atomic radii become cylinders or needles. So atoms as they exist around us cannot exist because we think of atoms as having that nice little Bohr radius where it's like electrons are zipping around in like spherical distributions or radial distributions. No, they become cylinders, which is very, very, very strange. So atoms can't exist, or chemistry that we know it can't exist near neutron stars. So molecules themselves melt close to neutron stars because of the reshaping of atomic structure. So that means that the magnetic fields themselves become so very strong that they actually stress the crust of a neutron star and fracture it. So remember the density is incredibly high, but that's enough to actually push the nuclei apart because they're being deformed and they stress and fracture them. That makes a star quake, which then emits huge amounts of gamma rays. Those gamma rays then make a fireball, which then get trapped by the magnetic field. And that trapped magnetic field, then the light becomes trapped, and as the star rotates, becomes a burst of gamma ray burst, or a millisecond gamma ray burst. So you get these whips of things that you have of a series of gamma ray bursts that go bip, 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 in many times in milliseconds. So as it comes in and out of view as it rotates. So these things last only a few seconds and have been observed by the Fermi Gamma Ray Telescope as well as the Swift Observatory as well. So magnetars are the most powerful magnetic field in the cosmos. So once again, we talked about the equation of state, and like we said before, you don't get it's just like we have before. We have the ideal gas law, which relates to pressure, density, and temperature. No, that's not. You can't have that on your neutron star. And what about the relativistic electron degeneracy pressure? Nope, you don't get that either. There's something else going on inside of neutron stars. In fact, the study of neutron stars and their equation of state is an active area of research. And nobody really knows exactly what the equation of state is, because you have to take into account many, many things, such as general relativity, quantum chromodynamics, superconductivity, superfluidity of matter. And you can't even make these materials on Earth. I mean, it's impossible. So the only way to observe them is by finding things, but those things are hundreds of parsecs or thousands of parsecs away. So the equation of state is strongly dependent upon the size and observed temperature of a neutron star and rotation rate. So one of the important things that astronomers can do to understand neutron stars is simply find the radius of a neutron star. And there's not many that are close, but there is one that is very close, that's relatively close, that people keep trying to study in order to get it, and we'll get to that soon. So the structure of a neutron star inside, remember we talked about the sun, it has a core structure and so forth. But the structure of a neutron star is really fascinating because this thing's only a couple miles, it's only 10 miles across. So what does it kind of do? Well, with these incredible densities, we get this very strange crust. And the crust, it's a solid. This thing is a star that is a solid. And the surface is basically an iron nickel solid at the crust, which is about just a half a kilometer thick. And it is a thick crystalline iron nucleus crust with electrons that go around. So you get just basically a hot ionized gas of 1,000,000 Kelvin. And it's a hot ionized gas that's a solid, which is really weird to think. Is it a gas? Is it a crust? What is it? It's kind of a weird thing. Inside of there is an inner crust of electrons and neutrons about a kilometer or so thick. And then there's an outer core and an inner weird core. And there should be these weird superconducting states. But recently, in 2017, there was a fascinating study that actually kind of got at what these states can really look like. So the surface of the neutron star is an ocean of ions or a crystalline crust. The ocean would be an electron gas with a crust of ions across it. And then the outer crust would be a crystal of iron and silicon nuclei with an electron gas. Remember, the electrons stay a gas, but where the nuclei would be thick. And then the inner crust would be more neutron rich. And then you get this weird phase called nuclear pasta. And it's not some flying spaghetti monster thing. We'll talk about that in a second. But inside, between the crust where it's actually nuclei, inside of the core, there are no longer any nuclei. It's just so dense that nuclei don't even exist, and you just simply have one big nucleus. So the inner 9 kilometers is essentially a uniform nuclear matter, where it's just a sea of touching protons and neutrons, mostly neutrons and electrons. So that's what's interesting. But what do we mean by this nuclear pasta thing? And this was a study done by Kaplan and Horowitz. It was shown in the Review of Modern Physics in 2007. And there's the link in the archive before, but I'll get to it a little bit more. So what happens is that there's a slice through it, and so the outer crust is neutrons and electrons, and the inner crust is nuclei and electrons, and then the inner crust is neutrons, electrons, and nuclei. And then the outer core, you don't have any nuclei anymore. It's just neutrons, protons, electrons, and muons. And then you have weird stuff, exotic phases in the inner core. But there's a very strange thing that happens in the green middle region right in there. It's called nuclear pasta. And where it actually goes to this very, very strange phase where you have, let's say, in the inner crust, which is that upper level, but between the mantle and the inner crust, you start with these pure neutron fluid, which is the greenish area, and you have a neutron-proton superfluid. So you have pure neutrons moving around, and then a neutron-proton fluid that's in the yellow dots. And eventually those things become larger and larger because the proton-neutron fluid has to actually get pushed together at higher and higher densities. Eventually the neutrons and protons become stretched into a pasta-like phase, such that you have just neutrons and protons in like tubes, and that's their phase. So it's like an atomic nucleus in the form of a cannoli, or a pasta, or a mastoci, or a ziti. And deeper in, the nuclei then form sheets, like lasagna sheets of nuclei. So you have an atomic nucleus in the form of a lasagna pasta. And deeper in, you start to swap it out, and it becomes pure neutrons in the core, and with some isolated protons. But then eventually you don't get any more isolated protons because the density is too high for individual protons and electrons to exist, and they're forced into neutrons. So it flips, and you have pasta, a lasagna pasta of just pure neutrons, and then it becomes a pasta of cannoli of inverted pasta, where then you eventually get down to a pure fluid of neutrons and protons in the core. So you have these really strange states, very, very, very strange states. And they go into exactly how they look and how they shape, and it's a fascinating article that I invite you to go to. And hit that AstroBytes article that I put on the link there. It shows you what the various things look like. But basically, the nuclei deform. They're no longer nuclei. The strong nuclear force has very strange behavior in these densities, and the individual protons and neutrons bind together not as spherical nuclei, but as spaghetti or waffle or lasagna type nuclei. So we no longer have anything that looks like, oh, this nuclei with next to that nucleus. No, the nuclei are basically huge numbers of protons and neutrons that form spaghetti and waffle type structures or lasagna type structures, which is really strange. And so then we get this strange of appearance of a neutron star itself, and where you have this tiny atmosphere, a crust and an inner crust, and who knows what's going down in the core as the neutrons and everything break down to become quarks and individual quark things. And neutron stars are really hairy, is the end thing. Nobody really knows what's going on inside of them. They're incredibly hairy objects, but they're the most exotic possible state of matter in the cosmos. Black holes are really simple, as we'll see next time, but neutron stars are incredibly hairy. So there's a bit about neutron stars, and next time we'll talk about pulsars. See you soon.